Welcome to the second stage of learning calculus with me, everyone. Today we are going to discuss the topic continuity. So, what does it mean to say that something is continuous, or what is the meaning of the term continuity? So, the very first thing that comes to my mind when I come across this word continuous is a graph that looks like this. You say that this is continuous, and something that is not continuous may look like this, something that breaks in between. Okay. So if I give you a function that looks like this, let's say for example a parabola, you know that the graph of a parabola, it looks like this. You see that the function or the graph of this fx is equal to x square does not break at any point. So you know that this function is continuous at every point. So that gives us an intuitive answer. But given any function, you cannot keep on drawing the graph of that function to estimate the continuity of that function at the points given across. So it is not feasible to draw the graph because it's not sometimes easy to draw the graph. So we need to have a concrete definition of continuity so that we can use that definition and estimate the continuity of functions. So let us look at the definition of continuity. What does it mean to say that a function is continuous at a point? So a function f is said to be continuous at a point a belonging to the domain of f. Of course, it has to belong to the domain of f if there are two properties that are satisfied. The first property is that the limit of this function as x tends to a should exist. Now, we have already seen what is the meaning of the statement limit exists. So when you say that the limit exists, it means that the left-hand limit should be equal to the right-hand limit, that is limit of fx as x tends to a minus should be equal to limit of fx as x tends to a plus. The second thing is that this limit, if it exists, it should be equal to the value of the function at that point. I'm going to elaborate on this. The second thing is something called as a continuous function. When do you say that a function is continuous? So a function is said to be continuous, a function f is said to be continuous. You give the adjective continuous to a function if it is continuous at every point. If it is continuous at every point. So we have looked at the two definitions of continuous or continuity. The first thing is at a point and the second thing is in the entire domain. So there are several examples of continuous functions. The first one is, let's say, a polynomial. Every polynomial is a continuous function. For example, we just now saw x square, or maybe you can say x cube. So the graph of x square looks like this. The graph of x cube looks like this. You can also have trigonometric functions like sine and cos. So you have a sine x and cos x. These are also continuous functions that the graph looks like these. Also, other category of category of continuous functions are the exponential ones, e raised to x or 2 raised to x, etc. These are something that looks like this. I missed one more very important continuous function. It is log x. So the graph of log x looks like this. Like if this is the x-axis, then the function log of x looks like this. You see that it does not break at any point in the domain. Now, given any function f of x, there are two things that can happen. Either the limit of the function as x tends to a exists, or it may not exist. If it exists, you say that it can either be equal to f of a or it may not be equal to f of a. In the first case, you say that the function is continuous at the point a. In the second case, you say that the function is discontinuous at the point a. This type of discontinuity is called as a removable discontinuity. It's called as removable discontinuity. In the second main case, again here, there are two things that can happen. The limit may not exist because the left-hand limit is not equal to the right-hand limit, or there is something worse that can happen. The limit is actually equal to infinity. So in this case, in both the cases, you say that the discontinuity is irremovable. You say that the discontinuity is irremovable. Some people also call it as essential discontinuity. Okay, so there are two types of discontinuity, as you can see right now. There is something called as removable discontinuity, and there is also something called as irremovable discontinuity. Now, I will also show you how the graph of the function looks like in all these four cases. In the first case, the graph of the function may look something like, this, a graph that does not break at any point. In the second case, the graph may look like this. There is a function that is continuous up to a certain point, and then it breaks at a certain point, and there is a hole in the graph of that function, and the piece of that graph is somewhere above or below. So this type of discontinuity is called as a removable discontinuity. It is called as removable because you can always move this point and redefine the function so that the function becomes continuous again. Okay, what happens when the left hand limit is not equal to the right hand limit? In such cases, the graph may look like this. So there is a function, maybe something like that looks like this, a parabola up to a certain point, and then instead of beginning from there where it stops, it begins from somewhere else. So the left hand limit is not equal to the right hand limit over here. Why is it so? I'll tell you. The left hand limit is actually over here, and the right hand limit is actually over here. And you can see clearly that they are not equal. Now, in the last case, which is the worst case, the function's graph may look something like this. Let's say, the graph of the function is shooting to infinity when the value of x is approaching 0. So here you can see that the limit of fx as x tends to 0 is actually infinity. It's shooting up to plus infinity over here. We will be solving one problem from each of the above types, the 4 types that we have. Let us begin with the first type, that is a continuous function. So in exam, if you come across such a question, discuss the continuity of fx, which is defined, in a piecewise manner over here. This is called as a piecewise definition because in the first piece, that is 0 to 1, the function is x square, and in the second piece 1 to 2, the function is 2x minus 1, a parabola in a straight line. So when you are asked the question, discuss the continuity, they are asking you whether the function is continuous. It means to check whether the function is continuous in its entire domain. So here the domain of the function, as you can see, is 0 to 2, as the variable varies from 0 to 2. You can see that in the first part the function is x square and 2x minus 1 in the second part. These both are polynomials, and hence the function is continuous. The function is continuous at every point in the domain except for x equal to 1, which needs to be checked. Since the function is defined piecewise and it is breaking at the point x equal to 1, we need to check the continuity of the function at x equal to 1 using our definition instead of simply saying that it is a polynomial. If it were the same polynomial on both the sides, the first piece as well as the second piece, you could have directly said, but here the function is breaking at the point x equal to 1. So you need to check the function's continuity using the definition. So let us check the definition. Since the function is defined piecewise over here, always check the limit, the left hand limit and the right hand limit, because the function is different on the left side of 1 and on the right side of 1. On the left side of 1 it is x square, and on the right side of the 1 it is 2x minus 1. So we need to check the limit first using the left hand limit and the right hand limit. Okay, so let us check the left hand limit. The left hand limit is limit x tending to 1 minus f of x. In this case, f of x is x square. So it is limit x tending to 1 minus x square. And you just need to substitute 1 over here, and the answer is 1. Also, the right hand limit is limit x tending to 1 plus f of x, which is limit x tending to 1 plus, in this case, f of x is actually 2x minus 1. I substitute 1 over here, I get 2 into 1 minus 1, which is 1, which is equal to the left hand limit, and hence you can say that the limit as x tends to 1 of fx exists, and that is equal to 1. You don't need to say that it exists, you simply need to say that it is equal to 1. According to the definition of continuity, as we had seen earlier, the first point is done. Now we need to check the second point as well. We need to check whether the function is, the limit that we have just now found is equal to the value of the function at that point. So now you can say that f of 1, which means the value of f at 1 is here in this case. As you can see, it is equal to the equality of x with 1 happens at the second piece. And for that, it is 2x minus 1. So how do you find that out? You just need to plug in 1 into x and you get the answer as 1. So here it is simply 1, which is actually equal to the limit of the function at the point 1. So you say that the function is continuous. The function is continuous at 1 as well, and hence the function is continuous in the entire domain. Okay, let us now move on to the next question. We have covered the first type, which is the definition, the example of a continuous function. We now move on to the next, discuss the continuity of fx. Again, here we say the same thing, the function is continuous. Okay, here you can see that the domain of the function is the entire set of real numbers. It is because the function is defined as x minus 2 the whole square plus 0.5. This is actually a parabola which is shifted and then again shifted upwards. And this is a parabola for every value of x which is not equal to 1, which means that it is taking the entire set of real numbers but not equal to 1. And here, exactly at x equal to 1, it is defined as 1, which means f of 1 is equal to 1 over here. Now, so you say that the function, since it's a polynomial for every x not equal to 1, it is continuous. So you say that f is continuous everywhere in R except for x equal to 1, which needs to be checked, So now let us check. Now this is not a piecewise defined function because even though there are two parts of the function, there is no left part and the right part. So all you need to do is go by the definition of continuity and just check the limit of the function as x tends to 1. So the limit of the function as x tends to 1 is simply x minus 2 the whole square plus 0.5 with 1 substituted over there. So you get 1 minus 2 the whole square plus 0.5, which is going to be minus 1 the whole square plus 5, which is 1 plus 5, 1 plus 0.5, which is 1.5. Let us also check the second point of continuity, of the definition of continuity, which is f of 1. F of 1 is simply written as 1 over here, as we have seen, which means that this is not equal to the limit of the function fx as x tends to 1, which means that the function is not continuous at x equal to 1. Let us understand this with the help of the diagram. You can see that the function is breaking at the point a. The left hand limit and the right hand limit are the same. The limit exists, but it is not equal to f of a. Let us now look at another example. Here again, the question is discuss the continuity of fx, which is x square in the first part of the domain and x minus 2 in the second part of the domain. Here also there is a piecewise definition of the function. So you can say that the domain of the function here is 0 up to 3 by 2, the closed interval. As you can see that the first point is 0 and the second point is 3 by 2. I'll modify the question a little bit. Okay, so 3 by 2 is included over here. Now, you can say as usual that the function is continuous in the first part as it is a polynomial, f of x is equal to x square. And it is a polynomial in the second piece as well. But something happens at the point 1. It is breaking at the point 1, so we need to check the continuity of the function at x equal to 1. As I have already explained earlier, because this function is defined piecewise, you will have to check the left hand limit as well as the right hand limit. Now, the left hand limit of the function is limit of fx as x tends to 1 minus, which is in this case x square. As you can see, on the left side it is x square and on the right side it is x minus 1 by 2. So x minus x tending to 1 minus, you just need to substitute the value and then the answer is 1. Also the limit of fx as x tends to 1 from the right hand side is the limit of x minus 1 by 2 as x tends to 1 plus, just put there 1 over there and you get 1 minus half and you have half. You can see that the left hand limit is not equal to the right hand limit. The left hand limit is not equal to the right hand limit, and therefore you say that the limit of fx as x tends to 1 does not exist. You don't even need to talk about the second point because the first point here is not satisfied in the definition of continuity, and hence you can say that the function is not continuous at x equal to 1. You can say that it is continuous in the entire domain except for x equal to 1. Okay. This is how the graph of the function looks like. The left hand limit exists and also the right hand limit exists, you can see, but they are not equal to each other. The right hand limit is way below than the left hand limit. They are not equal, and hence the limit of the function does not exist. Okay, let us look at the fourth example of continuity. This is actually the third example of discontinuity where you have an essential discontinuity. As you can see that the domain of the function here is 0 to 1, because 0 is also included in the domain and it is going from 0 up to 1, and 1 is also included. So as you can see that 1 by x is a continuous function, but something happens at the origin. So if you try to calculate the limit of the function as x tends to the origin, that is limit of 1 by x as x tends to the origin, if you try to substitute 0 over there, you get 1 upon 0. So it is actually equal to infinity. If I try to draw the graph of this function, it would look something like this. So the domain here is 0 up to 1, and the function's graph starts at x equal to 1, because it is 1 by 1 at x equal to 1, and then it starts shooting up towards positive infinity, and hence the limit does not exist. So you say that the limit of fx as x tends to the origin does not exist. It is actually equal to infinity. But this type of discontinuity is called as essential discontinuity, as I have already discussed earlier. So you say that the function is not continuous at x equal to 0, but continuous everywhere else. In the domain. That is 0 to 1. Let us look at another example. There will be a function which is a composite of two different functions. So remember that there is a property. The algebra of continuous functions says that if you have a function f which is continuous and a function g which is continuous, then f plus g, f minus g, f multiplied by g, f divided by g, provided g is not equal to 0, and f composed with g, they are all continuous. So basically a mixture of continuous functions is always continuous. So here you see that there is a mixture of two continuous functions. There is a sine over there, and there is an x square, a parabola over there. And these both come under the category of continuous functions, and hence this function is continuous. You can say simply like that. So you can say since sine x and x square are continuous, and composite of continuous functions are continuous or is continuous, you say that the given function sine of x square is continuous. Continuous means continuous in its domain. As you can see that nothing is mentioned over here, which means that it is defined everywhere in the set of real numbers. That is continuous in R. Let us look at one more example. You might get something like this. In this question, the function is already given to be continuous. You have to find the value of k so that the function is continuous at x equal to pi by 2. So as you can see that there is a k hidden over here. And this is a function which is defined on the entire set of real numbers. For every x not equal to pi by 2, it is defined this way. And for x equal to pi by 2, it is defined this way. So you just have to find out the value of k so that the function is continuous, which means that the function is given to be continuous. So all you need to say that since f is continuous at x equal to pi by 2, you can say that the limit of fx as x tends to pi by 2 is equal to the value of the function at pi by 2, which means that the limit as x tends to pi by 2 of the function given here is k cos x upon pi minus 2x. So I'm going to plug it in place of fx over there, and the right side is f of pi by 2. As you can see that the value of the function at pi by 2 is 3. So I plug in 3 over there. Now all I need to do is find out this limit and just solve the equation. So how do I do that? So k being a constant can be brought outside, and there is a pi minus 2x over there. So you need to do a little bit of a trick over here. So instead of x tending to pi by 2, you write there x minus pi by 2 tends to 0. On the numerator, you just have the cos x left, and just write that pi minus 2x equal to 3. So there is a slight substitution that you may have to do. Just call this as h. So let x minus pi by 2 is equal to h, which means that the value of x is now pi by 2 plus h. Also, note that since x minus pi by 2 tends to 0, the value of x minus pi by 2, which is h, also tends to 0. So I plug it in all these values in the limit over here. So I get something like this: k times limit h tending to 0 cos of, instead of x, I write there pi by 2 plus h. In the denominator, pi minus 2x. Now let us also calculate what is pi minus 2x. So you can see that the value of x is pi by 2 plus h. If I multiply 2 throughout, I get 2x is equal to pi plus 2h, which means pi minus 2x is going to be minus 2h. You just have to replace or swap the positions of 2x and 2h. So the value of pi minus 2x is minus 2h, which I plug in over here. Which is minus 2h. Okay, and that is equal to 3 as earlier. Let us now try to solve this. So it is k times limit h tends to 0. Cos of pi by 2 plus h is going to be sine of h. Why is it so? Using the ASTC rule. Because pi by 2 plus h goes into the second quadrant, and there only sine is positive. Oh, since there is only sine positive, and since the question was about cos, it is minus of sine h. And there is a minus 2h already sitting over there, which is equal to 3. Okay, the minus and the minus gets cancelled. The 2 comes outside, and you have limit h tending to 0, sine h upon h equal to 3. If you remember, we have discussed in limits, there were 4 standard formulae of limits, and this is one among them. So you get one using one of the 4 standard formula. So k by 2 multiplied by 1 is equal to 3, which means the value of k is 6. That's it. So these are essentially the 4 types of problems that you will be coming across in any kind of exam. You can have a function which is continuous, and when it comes to discontinuity, there are 3 different types. And always remember, whenever there is a piecewise definition, always go for the left hand limit and the right hand limit. Okay, that's it for today.